Okay, so this is series and induction. We're going to talk a bit about this. This is in quite a few different places, but it's in further maths in A level for most people in Britain here. So we can't talk about this without talking about this guy right here, uh, Mr. Johann Carl Friedrich Gauss. So the myth is, when Gauss was 7, his teacher wanted to go out of the room quickly and told the class that to add up all the numbers between 1 and 100 very quickly. And the teacher, of course, thought this would take them a long time, but Gauss had figured it out almost instantly. This is when he's age 7, so he's a young prodigy, and came up with the answer 5,050. Now, this is a pretty strange number to guess for a 7-year-old, so the teacher's like, how the heck did you do that? Now, what Gauss decided, or what the pattern was, he figured out a pattern right away. Now, you can start to see it if you look at the numbers at the beginning and the end 99, 2, 1, 100, 101. So you put these together, right? And so 100 plus 1 is 101, as you can probably see. And 99 plus 2 also going to be 101. So then the trick is, how many of these pairs are there going to be? And there is 50 pairs. So Gauss comes up with this idea that, well, this is going to be n times n plus 1 over 2, which is a very famous series. And you can have a look at that. So this is actually the first equation that we're going to be looking at. And so this is going to be where r goes from 1 to r to n is equal to this thing here. And you can check it out that if you do put the numbers in here. So he's going from 1 to 100 right now, right? So you get 100 in there, and then you're going to go 101 over 2, and you can see 100 divided by 2 is 50, which is going to be 50 pairs of 101, which is our answer, 5,050, which is how he came up with it. Now, that's pretty quick for a kid of 7, but I mean, again, he's a child prodigy, he's a savant, if you would, and so he added a lot to things. So what we want to remember from this is not necessarily a story, but it does help us to understand things, is this little bit right here. This is our first summation series. So the next thing is, what are we talking about here? So a series is just, we're quite familiar with a sequence, right? Just to sum up, I'm sure you've seen this before. The sequence is just has a pattern from each number to the next, right? So just for this one, it's just adding 1. For this one, it's just adding 3. And so that's a sequence. So the same rule applies for each term in the sequence. Now, a series is just adding the pieces of a sequence up, right? So just summing up all these pieces in between. So there's always a plus operator in between each of these things. And when we're talking about series, we're going to be using this symbol a lot of the time, and this is to denote summation notation, which, rhymes, which is, very fun, of course, but it's essentially just another Greek letter. This is capital sigma. It'll be handy when you're kind of reading this, and it's the same thing that goes with most mathematical operators or symbols that you don't know, is to have to say it in your head as you're reading it. Otherwise, these symbols just are kind of like blank spaces in your mind. So you need to make sure you're saying something as you're reading it. It's either sigma, or you could say the sum of. Okay, so let's look back at this summation notation thing. So what we have here, you can see that we have our big sigma up here. And so what this is saying would be, this is the sum of all terms defined by r. So it's just the number as it counts up. So this is like a counter, or if you're in computer science, it's like an iteration from 1 to 100 on this thing. And so we're going to count up, we're just going to add up all of the pieces from 1 to 100. This is the thing that Gauss did. And just as a reminder, that's what these two things are then. So this is the general equation right here for 1 to 100, whereas this one is going to sum up all the terms to n, which again is the sum from 1 to n. Notice here as well that you got an n minus 1 term, so it would count back all the way down to 1 this way too. Now this is quite useful, because this is actually, if you're thinking computer science here, this is actually only a runtime of 1, right? It's just one operation to get this thing. So breaking anything down into this sort of a piece is going to be quite useful, because this would run from 1 to n, which is a lot more operations, whereas this, you just punch it into the formula and we're done. We like these sort of things, these shortcuts, right? And we need to make sure to memorize this one because in most formula books this isn't going to be there. So this is kind of a key formula that we're going to have to memorize, okay? Right, so the next thing is to try to prove this by induction, right? Which is something that they're going to make you do a lot of in further maths. They love that sort of proof, but it is very useful proof because it does get us to n, right? And to get us to the nth term, a lot of the time it tries to prove it for each of these. So this is called proof by induction. This is kind of the weak version. At university, you can get a stronger version, but let's just review what we need to do for that. All right, step one. Prove it works for the first time. This is usually one, not always one, but pretty much most of the time it's going to be one for us. Which for our first case is a pretty simple summation from 1 to n is just 1 plus, that's it, just 1. So ting, that works, nice one. Next one, step 2, which is this, assume this works for the kth case. So we assume that this part here is true, and this is always going to be key to things because we're going to try to use these pieces again in the actual next step in the proof of this, okay? So which moves us on to step 3. 3, the try to prove for the kth plus 1 case. Now, what is this going to look like? So we'll show you how to do each of these steps here. So what we do, we're going to do a left-hand side versus right-hand side type of proof. So we're gonna, what is this gonna look like? Now we just put the same thing, the summation notation on the left side here, and we're gonna still go to R, but on the top here we're gonna go to k plus 1. We want that to be the next term in the sequence from the last one, so we're gonna say that that's equal to what it was before, so this thing here, which is essentially this guy, and you're just going to add the next term in the sequence, and because it's just R, that's going to be the same thing as k plus 1. So this is where we're at, so we're going to try to do this and make left-hand side equal to the right-hand side, okay? And so on the left-hand side here, and you can work both sides if you want to at the same time, but you don't have to, but on the left-hand side here, we're just going to use the formula that we had before. We're going to put k plus 1 in there instead of k. So we're going to go k plus 1, k plus 2, over 2. And we want that to be equal to, now that's the original one here, so that's going to be k times k plus 1 over 2 plus k plus 1. Okay? Now there's a few things here, and in the summation notations this happens quite a bit, that you can kind of see, well, there might be a lot of the same piece that you can take out. Now if we look here, got k plus 1 there, k plus 1 here, and k plus 1 here. So one of the things we're going to want to do is to get rid of the fractions if we can. So you can kind of add some nonsense here and just say, well, this is the same thing as if it was times 2 over 2, and that's just to get us a common denominator of 2 across the board here. That simplifies down to this. Now, again, there's lots of different ways to go through this. This is just one way that I'm doing here. So there's different logic that could take you at a different route, and it probably ends up with the same answer, which is just fine. And now you can see we have this k plus 1 we can take out of everything. So that's just going to leave us with k plus 2 on this side is going to be equal to k plus 2. Right? Nice and easy right there. So that's got rid of that k plus 1 and that k plus 1 and this k plus 1 because it's common to all of it. So you could cross them out if you want. You don't have to do that, especially in exams, but I always like to do it just to see what's happening there, like this. And so then you can see, if we've got it right there, that the left-hand side is equal to the right, left-hand side equal to right-hand side, left-hand side equal to the right-hand side. Therefore, true for the k plus, this is always tough to say, k plus 1 case. I feel like I've got a lisp at that point, k plus 1 case. And, but you always need to make sure you've got this statement at the end as well, right? Because if you don't have that, it tells them that you don't necessarily know what you're doing. So you need to, for exam purposes, make sure that you've got that line, and then you go on and say, therefore, true proven by induction, or something like that. And there we go. So that's proof by induction as to why it works. So Gauss was right at the age of 7, which is pretty awesome. More will come in the series, so we'll go into some more complicated cases in the next video.